In the 1970s, astronomers discovered that our Milky Way galaxy is moving. Drawn by great invisible forces, we were being pulled towards something, but we couldn't see what. Our final destination was hidden by the zone of avoidance, a region of the sky obscured by the gas and dust of the galactic disk, like a tiny raft adrift in a vast ocean. On a moonless night, we were caught up in the current, heading towards who knows where, and we weren't alone. For it wasn't just the Milky Way that was in motion, but all of our neighbours. Two astronomers were using the Parkes Radio Telescope in Australia to conduct a survey of distant galaxies, attempting, with their meagre observations, to reconstruct their movements. And around the same time, multiple teams of astronomers were observing the cosmic microwave background, the bath of radiation that survives as a relic from the early days of the Big Bang. Independently, both groups found the first hints of this great cosmic flow. The galaxies that were mapped seemed to share a common locus, their reconstructed velocities all roughly pointing in the same direction. As for the cosmic microwave background, its temperature across the sky revealed a bias. It was slightly hotter in one direction and slightly cooler in the other. Much of this discrepancy could be eliminated by considering the motion of the Sun around the core of the Milky Way. But after that subtraction, a residue remained, an unexplained source of motion relative to the ultimate cosmic reference frame, a speed amounting to hundreds of kilometers per second. It appeared as if the Milky Way and all the other galaxies in our nearby vicinity of the cosmos were being drawn to a particular spot, a specific location in the universe, as if tied by great invisible chains stretching tens of millions of light years. We couldn't see it, couldn't map it, couldn't figure out what it was. For decades, the best we could do was simply name it: the Great Attractor, a great source of inexorable motion, a persistent sink of gravity, a single point in the cosmos that pulls and pulls and pulls our entire galaxy and thousands others home to hundreds of billions of stars and countless planets, drawn to the Great Attractor like a helpless moth to a flame. And yet, no matter how odd this may seem, this is not an unusual situation in the cosmos. For the universe is far from static. Every object within the universe is in a state of restless motion, from the orbit of the Earth around the Sun, to the Sun's drift within our galaxy, to the hurtling of the Milky Way towards the Great Attractor. And that is not even the largest example in the universe. For the Great Attractor turned out to be just the tip of a far larger cosmic iceberg flowing across the sky, vast cosmic structures and motions dwarfing anything we had ever seen before. And so nothing is still. Everything is going somewhere. The question is, where? On September 23, 1999, the Mars Climate Orbiter lost contact with NASA as it approached the planet. The mission was totally lost, and it later turned out to have been down to a mistake, converting metric to imperial units. Even multi-billion-pound projects that are supposed to work seamlessly can fail, and that can also be incredibly frustrating when it comes to stuff you use every day, which is why some products are a great choice with their everyday earbuds. They are reliable, with a 32-hour battery life, multi-point connectivity to join with 2 devices at once, and brand new active noise cancellation, so you can even enjoy long flights without trouble. They have also been great for editing the audio for the videos too. They are comfortable to wear for long periods of time, which is especially important deep into the edit when wearing them all day long. And the quality rivals some of the big names in audio for almost half the price. The protective case cover is also a great stylish bonus and especially useful as it's easy to lose earbuds and it supports wireless charging. Our universe is defined by motion, and one way to describe the history of science is through our increasing awareness of the restlessness of the cosmos. For millennia, the brightest scientific minds in Europe and the Middle East believed that the Earth was perfectly still and that the heavens revolved around it. Those early astronomers busied themselves with attempts to explain and predict the motion of other objects, the sun, the moon, each of the known planets and the stars, and their predictions worked surprisingly well. But their cosmological system of motion wasn't perfect. In fact, it was an ungainly mathematical mess, relying on small circular orbits nested within larger ones, with some centered on the Earth and some centered on other points. And so, on his deathbed in 1543, the Polish astronomer published a radical reformulation of the old system that put the sun at the center of the universe, still and motionless, with the Earth set in motion around it, along with all the other planets. The reaction to the work was mixed. On one hand, it was a bold reshaping of the universe. On the other, it was arguably just as messy as the ancient system it was trying to replace. And on top of this, it introduced more than a few questions that had no easy answer. First and foremost, if the Earth was moving, how could we tell? We know we are moving on the surface of the Earth through a variety of ways. We can feel the wind against our face when we run, or watch as a distant goal draws nearer. So why don't we feel a great rush of wind as the Earth orbits around the sun? Or why aren't we flung off into the void of space due to the incredible rotation of our planet? It took centuries of science and the development of a theory of gravity for the full picture to come together. Today, we know that we don't feel the motion of the Earth because we are in motion along with it. And since the vacuum of space is just that, a vacuum, there's nothing for us to push against and betray that motion. But how can we guarantee that the Earth truly is in motion? Is there a standard reference? Indeed, one scientist assumed that such a standard existed, that there was a fixed frame of universal reference from which all motion could be measured. In crafting relativity, another scientist rejected the concept of a fixed universal ruler against which we could judge motion. Instead, all inertial motion was relative. The only way to measure your motion is in reference to something else. From this fundamental idea, the rest of relativity blossoms, the fabric of a space-time, the equivalence of mass and energy, and limitations of the speed of light, all of it. Imagine cruising in an unpowered rocket ship and encountering your friend doing the same. You are both in an inertial frame of reference, moving at a fixed speed. As you cross paths, you may declare that you are moving and that they are staying put. In relativity, they have just as equal right to state that they are moving and that you are the one who is standing still. These two perspectives are equally valid. Despite this, we can tell that the Earth is spinning because of the Coriolis force, which twists air streams around to form hurricanes and typhoons. Even if our skies were completely blank, with not a single star to be seen in the sky, with nothing left to measure except what we have right in front of us, we could still deduce the motion of the rotation of the Earth. But the movement of the Earth throughout the greater universe is another matter altogether. For that, we need to identify some other frame of reference, some other yardstick for us to measure from. Otherwise, we could rightfully claim, just like any other object in the universe, that we are motionless and that the rest of the cosmos every planet and star and galaxy moves about and around us. Thankfully, the universe itself gives us exactly the tool we need. The trick is that we don't live in a static universe, but an expanding one. The cosmos changes from day to day. In the past, it was smaller, and in the future, it will be larger. This allows us to write down a preferred frame of reference. And this preferred frame of reference is one that expands along with the universe, allowing us to measure motion relative to that. In other words, at large scales, the universe is expanding. On average, galaxies are getting farther away from each other with time. We can then define motion on top of that general expansion. Anything that deviates from the general outward flow of the universe is indeed special and unique. In the parlance of cosmology, this is known as peculiar velocity, and these velocities can range from a few hundred to a few thousand kilometers per second. Armed with this mathematical toolkit, cosmologists can begin to understand not just the rotation of the Earth or the orbit of our planet around the Sun, but the movement of the solar system with the galaxy and the action of the Milky Way within the wider universe. And so, without even feeling it, without even taking a single step, you will move an incredible distance through your life. First, there is the rotation of the Earth. Depending on where you sit on the globe, you could be whipping around at up to 1,600 kilometers every hour. Of course, if you happen to be standing on either geographic pole, your rotational velocity will be exactly zero. For most of humanity, which lives somewhere in the mid-latitudes between the poles and the equator, the typical everyday velocity is around 1,000 kilometers per hour. For a typical human lifetime of around 80 years or 700,000 hours, that gives a lifetime movement of around 1 billion kilometers, just due to the rotation of the Earth. But the Earth is also orbiting around the Sun with an average speed of 30 kilometers per second. Over your lifetime, that adds up to around another 80 billion kilometers of total movement. Of course, most of that is in a rough circle, so it's not like you're going anywhere with it. And the orbit of the Earth is not the end of our motion. The Sun, along with all the planets, asteroids, comets, and all the other denizens of the solar system, moves within the Milky Way galaxy. Most of that motion is a simple orbit around the galactic center, a journey that takes 230 million years to complete a single revolution. But in that time, the Sun travels an enormous distance, giving it an average speed of around 230 kilometers per second. And interestingly, that number is also profound evidence for the existence of dark matter within the Milky Way galaxy. When we add up the mass of all the luminous objects within the orbit of the Sun, even including generous allowances for all the stars and clumps of gas that we can't directly observe, there isn't nearly enough material to keep the Sun in a steady orbit. If there was no additional source of mass, the Sun's current speed should have assured that it would have been completely ejected from the Milky Way billions of years ago. But yet the Sun is still here, still orbiting, chained to the Milky Way by some invisible form of matter, dark matter, that lends its weight to the galaxy and glues everything together. In addition to its orbit around the center, the Sun also lazily bops up and down like a buoy in a dark ocean, a byproduct of the unstable gravitational influences of all its neighbors. Over the course of millions of years, the Sun rises thousands of light years above the galactic plane before plunging through it, reaching a minimum and starting the cycle anew. Currently, the Sun is plunging through a region known as the local bubble, a cavity blown out of the interstellar medium by a supernova detonation that went off millions of years ago. The bubble has a density less than one-tenth the average for the Milky Way, which is already low enough that it would register as a vacuum in a laboratory on the Earth. Our solar system entered the bubble somewhere between 5 and 10 million years ago and will continue to cross its 1,000-light-year expanse for millions of years to come. But that is far from the end of it. For against the backdrop of the expansion of the universe, our galaxy is on the move, and it's headed right for our nearest neighbor. Billions of years from now, our sky will be unrecognizable. The moon will be smaller, fainter, and more distant. The sun will be larger and brighter. All the familiar constellations will be gone, replaced with a new generation of stars in our solar neighborhood. And in that nighttime sky, one singular object will reign supreme, greater in majesty than any nebula, star, or planet. The Andromeda Galaxy. Right now, Andromeda is large, but not noticeably so, taking up as much of the sky as a fist held at arm's length. Within 2.5 billion years, however, Andromeda will dominate our nights, almost completely filling the sky. And it will not look like the Andromeda that we know today. In the far future, it will be gross and distorted, its previously simple shape twisted by tremendous forces of gravity as it begins to entangle with the Milky Way. A billion years after that, the sky-filling Andromeda will be ablaze with giant stars, as the gravitational interactions between the two galaxies will ignite a new round of star formation 1,000 times more furious than its present rate. And it will be billions of years after that, long after our sun has breathed its last, that the merger process between Andromeda and the Milky Way will end. The core of the new galaxy will glow with ghostly prominence in the sky, brighter than any other nighttime object. One by one, the giant stars will die, exiting the cosmic stage in a flash of supernova energies. If our planet survives the cataclysmic bursts, huddled against the meager glow of the sun's white dwarf, we will see our sky slowly fade. First, into redness, and then as the last of the visible stars disappear, into blackness. It was in the 1920s that a scientist made the remarkable discovery that the Andromeda Nebula, which had long befuddled astronomers, was actually an island universe in its own right, an entire galaxy sitting a staggering 2.5 million light-years away, over 10 times more distant than the furthest object astronomers had hypothesized could exist. But measuring the speed of Andromeda was not a straightforward exercise. Andromeda is simply too big. Training a telescope on it only revealed a small portion, with wildly different velocity measurements. And so it took until 1957 for an astronomer to finally provide a robust number. He examined the faint radiation emitted by neutral hydrogen, something known as 21-centimeter radiation. With careful radio measurements, astronomers could build up crude maps of the feeble signal sent out by this neutral hydrogen and examine any shifts in its spectrum. A redshift from the expected wavelength would indicate movement away from us, while a blue shift would signal motion towards us. And via this method, an average speed of -296 kilometers per second was arrived at, with an uncertainty of around 10 kilometers. A clear indication that Andromeda is moving towards us. But to complicate matters, that measurement didn't just include the motion of our galaxies moving together, but also the movement of the Sun around the galactic center. That must be subtracted out to give the true galactic motion. And that number is right around 100 kilometers per second. But of course, now that we know the number, there is freedom to choose the frame of reference. We could say that the Milky Way is still, and that Andromeda is racing towards us, or that the Milky Way is rushing towards it at a great speed, but in the frame of reference that respects the expansion of the universe, our two galaxies are actually both moving towards each other, heading towards a common gravitational center. But motion towards us didn't necessarily mean that we would collide. Astronomers can typically only measure the radial motion of a galaxy, the component of its velocity that is pointing either towards or away from us. Lateral, or side-to-side, motion is much more difficult to measure. It wasn't until 2012 when a team of astronomers used a space telescope to measure the velocities of thousands of stars within Andromeda that we had our first clear picture of its true three-dimensional course, and it was then that we realized that we really were on a collision course. The fun begins in as little as 2 billion years. As our galaxies draw closer, their immense gravitational interactions will begin to distort and reshape them. The cause is the same physics that governs the ocean tides on the Earth. The parts of each galaxy that are nearest to each other will receive a stronger gravitational pull than the rest, while the parts on opposite sides will receive the weakest gravitational pull. This causes a tidal force that will stretch each galaxy. Sometimes, entire spiral arms can detach from a galaxy, causing a phenomenon known as a tidal tail, an expanse of intense star formation stretching tens of thousands of light years. Between the galaxies, a bridge of gas and stars often develops, as if the galaxies are reaching for each other. When the merger event finally happens in roughly 5 billion years, it will not be like a sudden car crash. Most of the volume of each galaxy is nearly empty space, consisting of nothing more than a thin spread of plasma stretched between the stars. While the gas itself tangles up on itself, forming shock fronts and complex waves of disturbances, the stars themselves simply pass by each other like two swarms of bees. But that does not mean the stars will go unharmed. In the midst of a galaxy merger, stars will come dangerously close to each other, not enough to pair off and merge together, but more than close enough to disrupt their orbits. In short, everything will become chaos, the flat plane of the galactic disks replaced with a tangled mess of complex, overlapping orbits. Most stars will survive in the new reality, but some will be scattered, receiving boosts of energy from nearby encounters, flung away from their galactic home forever. The first merger pass will take more than 100 million years to complete, and will repeat several times over a few 100 million years, with each cycle of collision, interaction, and separation growing progressively shorter. Each one of these interactions will lead to a fresh round of star formation as gas compresses and fragments. At its peak, the star formation process in the merged galaxy could reach over 1,000 times its present-day rate. And so for a brief moment, it will be beautiful. The merged galaxy adorned with millions of newborn stars, blazing bright white and blue, a dazzling release of the titanic energies that powered the collision. But then, sadly, comes the tragic end. Galaxies have only a limited supply of gas to turn into new generations of stars. Left alone, a galaxy like the Milky Way can steadily sip on its reserves for over 100 billion years. But the act of the collision burns far too hot, quickly depleting reservoir after reservoir of gas in the intense rounds of star formation. Once those stars die out, there will be relatively little left to form new ones. and the only remaining stars within the galaxy will be the long-lived dwarf stars, small and dim and red. The merged galaxy, some call it Milkomeda, will become a giant elliptical, a large, red, ovoid, incapable of substantial star formation and doomed to simply pass the days watching its population of stars drop one by one. Of course, this is all hypothetical, our best guess as to how this massive event will unfold, and some of the most recent simulations have raised the possibility that it may not happen for another 8 billion years, if at all. Astronomers cannot, of course, watch galaxy mergers play out in real time, as the process takes hundreds of millions of years to complete. Instead, what we have are snapshots, the beginning of a merger here or the end result there, a kaleidoscope of catastrophes caught in this specific moment in time. Take the Mice galaxies, a pair of interacting galaxies sitting 290 million light-years away. So named because their long tidal tails make them look like two mice nestled together, the galaxies have just begun the merger process and the ensuing gravitational distortions. And in 2023, astronomers used a space telescope to observe ARP 220, a pair of galaxies caught mid-merger, sitting 250 million light-years away. The merger triggered a round of star formation, so intense that the galaxy now shines over 100 times brighter than the Milky Way. But already star formation has shut off. What we are currently seeing is the afterglow of the already ignited stars. Throughout the universe, astronomers see countless galaxies caught in the act in a variety of stages and interactions. There are galaxies colliding head-on and others just glancing by each other. Sometimes they are perpendicular, and sometimes they are slamming their spiral arms against each other. Sometimes more than two are caught in a struggle for gravitational dominance. And so the process of galaxy mergers began billions of years ago, even before the galaxies themselves arose. And it will continue into the future. For the journey of the Milky Way does not end at its merger with Andromeda. Our motion through the universe is far from over, and it's towards a direction that we barely understand. Sometimes mathematics can be a crystal ball that lets the careful observer peer through the distant reaches of space and time. And sometimes that crystal ball begins its own story in a space and time far, far removed from modern-day cosmology. Take the wide-reaching consequences of the work of a mathematician, although he didn't know it at the time. Instead, as a government official in revolutionary France in 1792, he was more interested in working out optimization of problems in the transportation of goods. Several decades later, a great pioneer took earlier mathematical work and expanded on it, generating an equation that has since found use in a variety of economic settings. For example, in figuring out the most efficient way to move resources between mines and factories. In the midst of World War II, a mathematician took this work to the next level, extending and applying the equations to the thorny logistical problems faced during wartime. But finally, in a beautiful example of the universality of physics, in the 1970s, a cosmologist realized that the same equations could be used to describe the efficient movement of mass in the assembly and formation of galaxies. Coming from a humble background, the son of a grain exchange worker and a homemaker, this scientist would go on to study at a prestigious university and eventually become a giant in the field of cosmology. Though in the early days of research in the 1960s, cosmology was not widely considered a serious field of study. It was known that the universe was expanding and that the Big Bang picture was likely correct, But there was so little observational data available that most astronomers considered the field a dead end with no serious future. But instead, this researcher pushed on and pioneered almost every aspect of modern physical cosmology, from the growth of structure to the earliest moments of the Big Bang, work that would earn recognition in later years. And completing the circle, it was two astronomers who followed up on this pioneering work and finally turned the so-called mathematical equations into a cosmological crystal ball. They found that they could take the present-day positions of galaxies and combine that information with limited information of their velocities to transport those galaxies back in time. The trick behind the approach is that we know how galaxies move. They are influenced by their mutual gravitational attraction, and we know how gravity works. So this technique allows cosmologists to take the current state of a collection of galaxies and compute where they should have been in the past. It's not a perfect technique by any means. Every step backwards in time introduces ever larger uncertainties, and the technique can't go all the way back to the Big Bang, but it does work. With this method, researchers have released continuously updated catalogues mapping out tens of thousands of galaxies around the Milky Way, along with their positions billions of years ago. That information allows them to reconstruct the motions of galaxies through cosmic time, not just into the past, but into the future, giving them the ability to predict where the Milky Way is headed. And it's through this technique, a combination of intense, careful observations and clever mathematical crystal balls, that we can finally understand the shape and influence of the Great Attractor, and what our ultimate fate in the universe will be. The expansion of the universe allows us to construct a preferred frame of reference from which we can judge all motion, its movement, relative to the general expansion flow. We can create detailed velocity maps of nearby galaxies to attempt to ascertain that general flow, a laborious and error-prone exercise. However, thankfully, the universe itself gives us a snapshot of that